This is Chapter 15, Lecture number 1. We're going to be discussing energy and how they relate to a chemical change. Essentially, it's going to boil down to endothermic and exothermic reactions. Campfires, the sun, if you rub your hands together, they all produce energy, which means they release heat. But if we melt ice or boil water, we have to absorb heat. So this topic today deals with heat. We have a law of conservation of energy. In any chemical or physical process, energy is neither created nor destroyed. All of the energy can be accounted for as kinetic energy or potential energy. Kinetic energy is energy of motion. Potential energy is stored energy. Gasoline is stored chemical potential energy. We control the explosion in the car's engine, and the potential energy of the gasoline is turned into useful work or kinetic energy. Energy is the ability for doing work. So here we see the girl is holding the ball on top of a ledge. That is potential, and as soon as she releases the ball, it is turning into kinetic energy, energy of motion. We're also going to be dealing with heat in this chapter. Heat is given the symbol small q. Heat is the transfer of energy from an object to another because of a temperature difference. Heat will always flow from a warmer object to a cooler object until the temperature of both are the same. We have a term called heat capacity. It's the amount of heat needed to increase the temperature of an object exactly 1 degree Celsius. It depends on the mass of the object and the chemical composition of the object. For instance, a steel girder has a greater heat capacity than a steel nail. So the greater the mass, the more heat is required to raise the temperature 1 degree Celsius. Also, a puddle may be cool on a sunny day, while a sewer cover may be too hot to touch. So the composition of the object is also important. Water takes a long time to heat up, whereas metals take a short time to heat up. So that we are dealing with the same amount of an object, instead of talking about heat capacity, we talk about specific heat. Specific heat is the amount of energy required to raise the temperature of 1 gram. Here I say water, but it can be anything. 1 degree Celsius. For water, the specific heat is 4.18 joules per gram, and it can be a Kelvin or it can be a degree Celsius. They are interchangeable. So the specific heat of any substance is the amount of heat required to raise 1 gram of that substance by 1 degree Celsius. Water has a very high specific heat compared to other substances, which we can see in this chart down below. Water, 4.184 joules per gram degree Celsius. A metal, like aluminum, is only 0.897. It requires a lot more energy to heat up water than it does to heat up aluminum. So metals generally have low specific heats, therefore it takes more energy to heat up water than to heat up a metal. Once heated, the water also releases a lot more energy or heat when it cools. So we have an equation for calculating heat. And it's not hard. It's Q equals mc delta T. Q is the joules of heat that are absorbed or released. M is the mass of the object. C is the specific heat of the object. And delta T is the change in temperature, Tf minus Ti. The final temperature minus the initial temperature. So let's start the worksheet and do a couple of conversions. Kelvin equals Celsius plus 273. So 33 plus 273 would be 306 Kelvin. Minus 10 plus 273 would be 263 Kelvin. And if we have to go the other way, 48 Kelvin equals degrees Celsius plus 273. So it's 48 minus 273, which is minus 225 degrees Celsius. You should be able to convert either way. So number one, show all work using ESA. The temperature of water, the mass of, increases from, what's the total amount of heat absorbed by the water. We start with our equation, Q equals mc delta T. The mass is 29.6 grams. The specific heat of water, we can use 4.18 joules per gram degrees Celsius from the chart on the page before. And the difference in temperature, 39.8 minus 12.7, is 27.1 degrees Celsius. Grams cancel, the degrees Celsius cancels, and we're left with joules. So on a calculator, when we do all the math, we get 3,353 joules, which is fine, but if we look in terms of sig figs, each of these numbers have 3 sig figs, so I'm going to have 3 sig figs. 3,350 joules. So we'll do the rest of the problems in class, and that will be it for today's lecture. So have a great night.